Welcome to our short course today titled Introduction to Machine Learning and Geomechanics, a comparison of classical numerical modeling to the new paradigm of machine learning. Our goal with this course is to essentially demystify machine learning for those that aren't familiar with it, and also give more information to those that are just beginning to use these tools. We hope to give you enough knowledge to understand the machine learning process at a high level and get started with applying these methodologies yourself. As for quick introductions, my name is Chris Thielsen, and this is my coworker, Dr. Wei Fu. We are engineers and consultants with the ITASCA Consulting Group. We've had the great fortune to work on some really fun and interesting machine learning projects over the past 3 years or so. Shown here on the screen is the schedule for today. So we'll start off with 2 presentations on the fundamentals of modeling, both physics-based numerical models and machine learning models that are based on data. We'll have about a 20-minute break halfway through the course, and then we'll finish off with 2 more presentations, focusing on the application of machine learning techniques in real consulting and research projects. If you have any quick questions before we begin, you can speak up now. Otherwise, I'll pass this over to Wei, who will start us off on our first presentation.
Now we will move on to our introduction to machine learning and surrogate modeling. Starting with an outline of what I will be discussing today, I will first go through the general fundamentals of machine learning, answering the immediate question of what is machine learning. Then we will dive into the machine learning framework or pipeline of building an accurate machine learning model. This largely consists of feature encoding and engineering, model selection and training, and model evaluation and tuning. The next topic will be an introduction to surrogate modeling, which is really a powerful link between the classic paradigm of numerical modeling and the new paradigm of machine learning. Data generation and sampling is an important aspect here. Then finally, I will go over how you can actually get started using these tools and end with some summarizing thoughts. At the right is a depiction of the various subfields of machine learning. Today, I will primarily be focusing on supervised learning. So, what is machine learning? Machine learning is the art and science of making computer predictions without explicit programming. This is also known as a data-driven subfield of artificial intelligence. Although these terms are sometimes used interchangeably, artificial intelligence is really the overarching field that encompasses machine learning, as well as other topics such as optimized search, natural language processing, robotics, computer vision, and game playing. Machine learning is focused on utilizing large data sets to make unbiased decisions. Often the goal is to either understand underlying data structure, which is denoted as unsupervised learning, or predict unknown information from large data sets, which is denoted as supervised learning. The objective of supervised learning is to create a function that maps an input to an output, based on example input-output pairs. The general idea is that we train a machine learning model on some data set with these example pairs to accurately capture the relationship between them. A final note that I will be repeating multiple times throughout this presentation is that the model is the data. This is a fundamentally different approach from numerical modeling, where explicit physical relations make up your model. Maybe an even more important question to ask, why is machine learning useful? Using machine learning, we can take advantage of the current era of big data. Shown in the top right is an estimate of the world's storage size. And for reference, 1 exabyte is equivalent to 1 billion gigabytes. As of 2020, it was reported that the global storage capacity is somewhere around 6,800 exabytes. One of the biggest things driving this is that automatic large-scale data acquisition is common in many industries today, geomechanics included. For example, many large mining operations have tens or hundreds of piezometers, surface and subsurface sensors, even satellite and drone imagery. The data is out there, and often it is either underutilized or sometimes unused entirely. An important takeaway is that more training data leads to a more accurate model. The more input-output pairs you have to train your model on, the better it will be able to correctly capture the behavior of interest. There are 3 big advantages of machine learning. The first is that machine learning models are extremely flexible and can learn highly nonlinear behavior. This is especially powerful when there is no explicit physical relation between your inputs and your outputs. The second is that machine learning models are extremely fast. It typically only takes milliseconds to make a single prediction, essentially in real time. Real-time results means you can easily check different scenarios for your inputs. This can further empower you to incorporate these models into simple, easy-to-use web applications, which I will be discussing later. The final point to make is that machine learning algorithms are domain agnostic, meaning that they can be applied to any scientific field or problem, granted that you have enough data to model the relationship of interest. Now let's dive into the general framework of machine learning. In broad steps, this consists of data preparation, model training, and model evaluation. These steps outline the process of building an accurate machine learning model, with data preparation taking up the bulk of the effort required. The first step is data preparation, which is the most time-consuming and the most important step. This consists of cleaning up messy data, fixing errors and incorrectly recorded data points, determining the best values to input for any missing data, homogenizing your data if it comes from multiple sources, properly encoding your features, which are the pieces of information associated with each sample in your dataset, and engineering new features using your domain-specific knowledge. The reality is that most real datasets aren't perfect, and typically a large amount of effort is required to prepare your dataset before it can be passed to a machine learning algorithm for training. A joke often said is that machine learning is 90% data prep and only 10% machine learning. And really, this gets back to the point that the model is the data. Now, how do we handle missing data? Before we can pass our data to a machine learning algorithm for training, numerical values are needed for each feature. Some common strategies include removing samples without enough recorded data, inputting a 0 or a sensible default value for each missing feature value, inputting some calculated value like the mean or median, or nearest neighbor imputation, where we select the nearest real value along each feature to fill in missing spots. Really, what you should ask yourself is why the data is missing for any given sample. Understanding that can help you figure out what the most appropriate strategy is. And ultimately, you want to use values that allow the model to better correlate your sample inputs to your outputs, or in the case of prediction, appropriate inputs that lead to a more accurate prediction. How you choose to represent your data to the model will have a huge impact on how your model learns and uses the learn relationship between your inputs and your outputs. Once all of your data is filled in, the next step is ensuring that all of your features are properly encoded. In general, your features are either numerical and already consist of numerical values, or are categorical and consist of a discrete set of labels. While your numerical features are ready to pass to a machine learning model, categorical features first need to be numerically encoded. The two primary ways of doing this are integer encoding and binary encoding, also called ordinal and one-hot encoding. Integer encoding involves ranking your categories in a sensible way, such that you encode some kind of physical meaning that the machine learning model can learn from. A good example of this might be labels of rock or soil hardness. Shown in the table at the right, we can assign these values to labels in a sensible way, ordering them from very soft to very hard. And in this case, we might consider using the median value of our range, medium, in place of missing values. However, sometimes we have categorical features that can't be ordered in a specific way. This could be something like the observed color, which doesn't have an obvious ordering. In this case, we can use binary encoding, which maps each discrete label over to an individual feature. A 1 is assigned if that label is present, and a 0 otherwise for each sample. While this allows you to easily encode features with no inherent ordering, it can also greatly increase the dimensionality of your model, which can lead to multiple issues that I will discuss later in the presentation. Once all your features are properly encoded, you can pass your entire dataset to a machine learning algorithm for model training and making predictions. However, before you do this, it's critical that you first try to add additional engineered features to your model. Feature engineering is defined as the manipulation and numerical encoding of raw features to create new features that are better predictors for the machine learning model. The idea is to apply your human expert domain-specific knowledge to the features that are already present, creating new features that are likely to be better predictors in your model. This is a really important reason why machine learning needs to be understood and applied by people in all scientific disciplines. And while you may think this introduces biased information to the model, it's really up to the model to choose what correlates best to the target. What we pass to the machine learning algorithm are simply its choices for the model inputs. The model will figure out in an unbiased way which features are the most relevant for predicting your target variables. With data preparation complete, now we can choose a machine learning algorithm to build our model. While many of these models don't take very long to build, There are many machine learning algorithms to choose from. Shown here is a list of some popular choices, including k-nearest neighbors, naive Bayes, support vector machines, tree-based models such as decision trees and the random forest model, and neural networks, which are widely used nowadays. Maybe it's obvious, but something that many people overlook is that these models do not actually exist before training. None of these are ready to go out of the box. These are all meta-algorithms that construct our model during training, using those input-output examples you feed it. That means that your model is uniquely constructed from your training set. Another important note here is that there is provably no single best machine learning algorithm. This is termed the no free lunch theorem, alluding to the saying that there's no such thing as a free lunch. Many of these algorithms are useful in different scenarios and for different data sets. For example, random forests tend to perform well on noisy data sets and can largely overcome overfitting. While I won't be going through the details of all of these algorithms today, I will say a few things about the k-nearest neighbors algorithm, which is often seen as the base case, or simplest machine learning model. I will be discussing random forests in more detail during my case study presentation after the break, and Wei will discuss artificial neural networks in his case study presentation. But first, a few more notes about machine learning models in general. Many of these models are a black box, where we essentially can't map out or even understand how exactly predictions are being made. However, over the past decade, efforts have been made to peer into these black boxes and try to understand how predictions are made. One such technique is called heat mapping, used on trained neural networks. While we can't often fully understand how the inputs are exactly being used to predict our outputs, that doesn't mean we can't validate the accuracy of the model or gain meaningful insights into what features may be largely controlling the predictions. I will discuss this further during model evaluation and in discussing feature importance. A final important note here is that machine learning models should only be used with inputs that are within the training range. A good analogy for this is fitting a high-order polynomial to some data points in 2 dimensions. You wouldn't fit a complex polynomial in a small range and then use that far outside this window. They tend to blow up outside this range and give values that are either very positive or very negative. Machine learning models are the same way. You can't train your model on inputs that are within a certain range and then try to make predictions using input values that are way outside this training range. The model would blow up and provide nonsensical results for the prediction. Something we've jokingly said about this before is to only play with sand in the sandbox. Now, a few things to say about k-nearest neighbors. This is a relatively simple machine learning model, where the main hyperparameter controlling how the model is constructed is k, the number of neighbors used to predict a new point. The learning is essentially a spatial mapping of your features in hyperspace. While this is pretty straightforward and easy to visualize in 2D, this can get more complicated in higher dimensions. Shown at the right here is a simple example. If we only had 2 features, one on the x-axis and one on the y-axis, you could plot your class labels and quickly see what the nearest neighbors are for a new point you wish to classify. If k is set to 3, the 3 nearest neighbors are looked at, and the new point is classified by taking the mode of your neighbor's class. The new point would then be classified as a green triangle in this example, class B. If k is set to 7, the 7 nearest neighbors are looked at, and the new point would be classified as a red star, class A. The next topic we'll move on to is surrogate modeling, starting with the question of what is surrogate modeling. A surrogate model is an engineering method to predict the outcome of some process rather than modeling the real process itself. In the context of what we're discussing today, a surrogate model is a machine learning model that has been trained using a synthetic data set generated by a numerical model. In other words, we're essentially replicating the response of a numerical model for some set of inputs and outputs with a machine learning model. This is useful for probabilistic analysis, numerical preconditioning, training and education, and for easy application by field practitioners. Of course, one of the biggest benefits is that you can generate your own nice and complete data set with a numerical model. This solves many of the issues related to having limited and messy data. However, there are still some important considerations, largely how to sample your feature space. A few options you have for this are grid sampling, random sampling, and Latin hypercube sampling, which tends to be the preferred method. Wei will discuss sampling in more detail in his second presentation. Another thing to consider is carefully choosing the range of values for each model feature. If your input ranges are too large, you may not be able to realistically generate enough samples in the entire range. If the input ranges are too small, then you may not fully capture the behavior of interest between your inputs and your outputs. One of the biggest questions that comes up in machine learning is how much data do I need? Unfortunately, you can't know beforehand exactly how many data points will be needed to get a good model fit. However, we can construct a learning curve to give us an idea of how well our model is performing as data is added to the training set. The idea is to slowly increase the number of training points and see how that affects the resulting model score, plotting the number of samples in your training set versus the score on a held out test set. The trajectory of this curve can help you understand how adding more training data might improve the predictive capability of your model. Another important thing to understand when generating your own data set is the central limit theorem. In short, uniform inputs do not lead to uniform outputs. Even though we will likely sample our features uniformly, the outputs end up being normally distributed when your inputs are combined in an additive way, and end up being log normal when your inputs are combined in a multiplicative way. Since model accuracy at a given output is largely a function of the quantity of training data at that output, this means that you may end up with poor predictions for low or high target values. This can be remedied by creating additional training data to infill the histogram. Shown at the right is an example of a model that we used to predict the bearing capacity of a many-layered soil body. The initial sampling of input features resulted in lower amounts of very weak and very strong bearing capacity examples. This was adjusted by adding more weak and strong cases to our training set, leveling out our target histogram before training the model. The real power with surrogate modeling is that we can replicate the results of a complex numerical model in real time. This enables us to put the model in a quick and easy to use web page for making predictions. An example shown here is a surrogate model of a simple rock slope in 2D, where hook-brown and slope geometry inputs are used to make predictions of the factor of safety for the slope. And in fact, the model is so fast that as we move the input sliders in real time, we can make hundreds of predictions of the factor of safety in height angle space and plot factor of safety contours within the web page as well. Feel free to point your phone at the screen to try out the tool. Once you've selected a machine learning algorithm, the next step is ensuring that your model will give accurate predictions, especially on inputs that it hasn't seen during training. The basic idea is to train your model and then make predictions on other data to assess its accuracy. You tweak the hyperparameters of your model, changing how the model is built from your training set to increase its predictive capability. You can pretty quickly see that training a machine learning model on your entire training set and evaluating it on that same set is problematic. The parameters of your model would be learned to simply regurgitate the values that it just saw during training. This defeats the whole purpose of training a machine learning model at all. You would end up with good predictions on your training set, but it would likely fail to predict anything useful on unseen observations. This is called overfitting. Overfitting can be alleviated by splitting your data set into a training set and a validation set. This could be something like a random 80% 20% split. The model is trained on the training set, and the hyperparameters are altered to perform optimally on the unseen validation set. While this is much better than using your entire training set for validation, there is still some risk of overfitting on the validation set, because the hyperparameters are tuned to perform optimally on that particular split of the dataset. This can be further helped by splitting your dataset into a training set, validation set, and a final held-out test set. The model is trained on the training set, evaluated and optimally tuned on your validation set, and then a final validation is performed on the held-out test set, of which the model has no knowledge of. While this further prevents overfitting your model, the big consequence here is that we now have less data available to train our model. Additionally, we're still optimizing the model on only a single split of the dataset. From this, one might naturally consider making multiple random splits and checking the score of each validation set. You can then take the average of each of these performance metrics as the overall score for your model. This is called cross-validation and is a much better method for evaluating your machine learning model. The idea is to split your data set into a training set and a validation set multiple times, where the validation set is a different subset of your data each time. This allows you to check the predictive capability of your model on your entire data set and tune your model to perform optimally on the entire data set as well, without overfitting the parameters of your model to a specific split of the data. After you have finished tuning your model, a final evaluation is performed on a held-out test set, of which the model has no knowledge of. Each of these folds, as shown in the image at the right, can either be random or stratified, ensuring an even class distribution in each fold. This is particularly important, as you wouldn't want a single class contained only in the training set or testing sets. Another thing to discuss is performance metrics. While there are some standard choices for what performance metrics to choose when evaluating and tuning your model, there are many choices available, and depending on the data you have and how you will ultimately be using your model, it may be more appropriate to create custom performance metrics. A list of popular choices from the scikit-learn library in Python is shown at the right. If your dataset contains discrete class labels, common performance metrics are accuracy and balanced accuracy. Accuracy is simply the percentage of labels that are correctly predicted, and balanced accuracy is the percentage of labels that are correctly predicted, weighted by the inverse prevalence or frequency of each class label. This is a useful metric for unbalanced datasets. You can imagine a scenario where we have two classes in a dataset, one of them making up 10% of our training set and the other making up 90% of our training set. If we had a very basic model that only predicted the second class for any set of inputs, using accuracy as our metric would tell us that the model is 90% accurate, which would be misleading for a model that hasn't truly learned anything and is unable to generalize. Balanced accuracy gives us a much better idea of the model's performance across all class labels. If your data set contains floating point values instead of classes and is a regression problem, the most common performance metric to use is R-squared. This is essentially a measure of the goodness of fit of a model. I'm sure many of you are familiar with R-squared if you've done any kind of curve fitting before. This is calculated as 1 minus the fraction of unexplained variance over the total variance. Another important concept to go over is the bias-variance trade-off. This is essentially another way of looking at overfitting versus underfitting your model. Bias is error from erroneous assumptions in the learning algorithm. If your bias is high, it will lead to underfitting your model and failing to capture the relationship of interest. Variance is error from sensitivity to small fluctuations in the training set. If your variance is high, it will lead to overfitting your model to the training set and failing to generalize to data it hasn't seen before. Shown by these two graphics here, it's really important to tune the hyperparameters of your model such that it accurately captures the behavior of interest while still being able to generalize to data it hasn't seen during training. Once your model is properly trained and optimized, it's possible to perturb the model and tease out what the important features are for predicting your targets. These are called feature importance methods. The two primary methods I'll discuss are impurity-based importance and permutation-based importance. Shown at the right is a picture of a typical feature importance chart, displaying the relative importance of each feature in the model. An important note on this is that the feature importance does not reflect the intrinsic predictive value of a feature by itself, but how important this feature is for a particular model. And really, this gets back to what Wei mentioned in his presentation. All models are wrong, but some are useful. This machine learning model you create is a custom tailored model based on your training set. If your model is very accurate, the feature importance can give good insights into what mechanisms may be controlling the output, but it's important not to get too hung up on it. First off is impurity-based importance. A major limitation with this method is that it can only be used on tree-based algorithms. When a tree-based model is built, the decision about which feature to split at each node uses a calculation of impurity, commonly Gini impurity. The importance of a feature is computed as the normalized total reduction of impurity brought on by that feature. The advantages of this method are that it's a very fast calculation and is typically one simple command that gives you these importance values for a tree-based algorithm. The cons of this method are that it greatly inflates the importance of high cardinality features. In other words, features with many unique values. Another big disadvantage is that it's computed from the training set and not the held out test set. The importances can be high for features that are not predictive of the target variable if the model has the capacity to use them to overfit. The second method is permutation feature importance. This provides a way to more directly measure feature importance by observing how random reshuffling of each feature influences model performance. The idea is that we first train our model and get a baseline prediction score. Then the values of a single feature are shuffled or randomized, essentially pulling that feature out of the model. The dataset then gets passed to the model again, and the new score is recorded. The difference between your baseline score and the new score is the relative importance of that feature. The more the model score decreases, the more important that feature was to make an accurate prediction of your targets. The advantages of this method are that it can be applied to any kind of machine learning model, and it's an efficient and straightforward way to calculate feature importance. Permutation feature importance can also be applied to a held out test set instead of your training set, giving you an idea of how important your features are for allowing your model to generalize. The only con of this method is that the importance of correlated features can be skewed low. If two features are strongly correlated and the values of one feature are shuffled, the model will essentially still have access to that feature through the correlated feature. Although really, you should try to remove correlated features from your model in general. That leads into the discussion on feature selection. Hopefully it's been obvious so far, but machine learning is an iterative process. As you work on improving your model, it's important to consider which features should really be included. Something you may have heard of before is the curse of dimensionality. In machine learning, you often deal with highly dimensional data. The problem is that it tends to be noisy and redundant. Given many samples, highly dimensional data can be computationally intractable, and most importantly, including too many features in your model can reduce the predictive capability of your model. For many machine learning algorithms, the main reason for this is that by including a large number of features in your training set, you increase the odds of including many weak predictors that make it harder for the algorithm to build your model from stronger predictors of your target. A good way to start reducing the dimensionality of your model is to remove features from your model that are strongly correlated. Strong positively or negatively correlated features essentially give your model the same information and shouldn't be included together during training. Typically, you would create a heat map, like the one shown at the right, of the Pearson or Spearman coefficient between each pair of your features, and remove one feature from each strongly correlated pair. You might also want to remove features that have a very low feature importance after training your model. Now let's discuss how you might be able to get started with using and implementing machine learning on your own datasets. The real ticket to entry here is learning Python. This is the most commonly used programming language for data science and applying machine learning techniques. Some often used libraries in Python for data prep and machine learning are NumPy, Pandas, scikit-learn, TensorFlow, and PyTorch. It's also useful to learn Git for version control and storing your projects on GitHub. The easiest way to get started is to choose a practical dataset to work on as a learning exercise. Even better if it's a dataset you're familiar with. Get your hands dirty, try things, and make mistakes. Tons of tutorials and resources exist online for learning Python and how to use these libraries. Looking through the documentation is a good first step and can provide many practical examples. And soon enough, you'll understand how to best apply these tools yourself. And now, some final thoughts to wrap things up. Most importantly, always remember that the model is the data. Data preparation is the most crucial part of the machine learning process. How you choose to represent your data to your model during training will directly affect the resulting model that's built. A machine learning model is only as good as the features that it is trained on. A commonly said phrase in computer science that certainly applies here is garbage in, garbage out. And finally, machine learning is not meant to replace numerical modeling, but complement it. There will always be a place for fundamental mechanics-based understanding of Earth materials, and numerical modeling will continue to be useful. Machine learning is simply another useful and necessary tool in the engineer's toolbox. And with that, I would be happy to take any questions. Thank you for listening.